Okay, good afternoon, everybody. My name's Eric Evanchik, and you are in open sourcing automotive diagnostics. Hopefully that's where you want to be for the next hour or so. But it should be fun. Just a little quick intro to me and what I do. Spent the last few years kind of hacking cars for a living, I guess. Run a little company up in Canada called Linklayer Labs that has developed some open source hardware tools, one being a CAN bus to USB tool that's quite relevant to this talk. Some other stuff not very relevant. As of very recently, I am actually a research consultant with Atretis Partners. We do all kinds of security consulting and research for folks with a big focus on mobile and embedded and also automotive stuff. And I also write for the blog Hackaday, which I just have to give a shameless plug to Hackaday. If you're not familiar with Hackaday, hackaday.com, check it out. We got lots of cool hardware hacks. But a quick outline of what we're going to do today. We'll do a little overview of in-vehicle networks for those of you that are not terribly familiar with them. I like to ask, is there any automotive industry folks in here? Don't be shy. We got one automotive, okay. Hopefully you won't be bored, but we'll do like a little overview of what's actually in a car nowadays, and then we'll talk about diagnostics, main theme, and then we'll go over the tools. We'll do a little tool release of what I've been working on and why I'm here, more or less. We'll demo that a bit and do some conclusions. But let's start with a disclaimer. You can brick, i.e. render useless a car via diagnostics. It is doable. You can erase firmware. It would not work out well. Your engine will not start if it has no code. You can also modify these systems via diagnostics, and they are safety critical systems, so you need to be cognizant of that. And some diagnostic actions, things like maybe changing VIN numbers or odometer values, might be illegal where you live, and that would be bad for you to do those. So this is a very proceed at your own risk, know what you're getting into. This stuff can be dangerous. In-vehicle networks. So it's important to understand the actual systems that we're looking at, and they're starting to get very complex. So an automotive network consists of a bunch of electronic control units, or ECUs. That's just what the industry calls them. These are all discrete computers typically. They have a microcontroller inside of them, some more hardware. They're running software to do everything from make your engine fire, to make your doors unlock, to deploy your airbags. It's just a huge amount of software and systems. It's probably the most complex distributed system that you would own. And a modern car, again, can have up to 100 of these in like a high-end vehicle, which is, you know, a lot of computers and a lot of code. And typically they're all connected via this thing called CAN bus, or controller area network. I'll refer to it as CAN from now on. This is a late 80s standard that came into place as just a nice way to let controllers talk to each other. It's really cheap to implement compared to some other things. It's quite reliable, and it works quite nicely. It has some problems with security, but it works quite nicely in general. And yeah, a modern car might look like that with all these different units floating around inside of it, and they can all be on different CAN buses, and then those buses might be bridged by different ECUs that act as gateways, so you get like a very complex network inside every single vehicle. The communication types in these networks, there's really two that you can break it down into. You have the operational communications, and this is what's happening usually the second you open the door or like hit the unlock button on your fob, or even on modern vehicles when you actually approach the car, it might start. And what's happening here is this is just communications between all these controllers so that they all know about what's going on, what the state is, sensor values, commands to lock and unlock things, things of that nature. And this is all happening on periodic broadcast messages. So a message might be a 10 millisecond broadcast. Every 10 milliseconds that's sent out, and everyone on the bus can look at it and decide whether they want to actually use that data. And they're all statically defined, so in one message, like byte 6 will always be the same thing. One example, when you start the car, you might take the key, turn it from off to accessory, and one byte might change from 0 to 1. And then whenever you go to run from accessory, that might be 1 to 2, then switch to crank, and now it's switching from 2 to 3. And that's the scheme that at least one company uses to encode that data. But that can vary because there's tons of sensors and inputs going on, so there's a lot of this happening. That's the operational stuff. Diagnostics, this is used at specific times and not normally. This only happens whenever you are intending it to happen, and it allows very special interactions with these controllers, but it acts as a client-server protocol. So rather than this periodic broadcast thing, you actually have to make a request and then you get a response back. So looks more like HTTP or something. You actually ask for data, and then the server comes back and says, here is your data. Operational stuff, again, it's broadcast, but from a security side, it's really easy to attack. We've seen a bunch of this in the past. This is one example from way back in 2010, which I think is the first stuff that was publicly released on this, where you'll see they've got the thing going 140 miles per hour, but it's in park, so that's clearly not real. What they're doing there is sending fake data on the CAN bus with the vehicle speed. They figured out what bytes they need to send for that, and the dash actually thinks the vehicle is going much faster than it actually is. They also added some fun text on the display as well. So it's pretty easy to attack because there's not much security on this, and it's extremely easy to do a denial of service on. Like, you just need to send a message with a low ID number, say 0, really quickly. And based on how the arbitration works on CAN bus, you will just shut the whole thing down and nothing can communicate and it all freaks out. And all your check engine lights come on and then you need to service your vehicle. Ask me how I know. But yeah, there's no persistence with this attack. You have to plug something in and then send a frame and then this happens. But once you unplug that device, it's done. You can't have any more fun. So you can either implant a device in there to do this, or you could maybe take over an existing controller in the vehicle. That's where we get to diagnostics. Diagnostics is used mostly for this part of the life cycle, so manufacturing. When the vehicle's actually set up, it might be used to update and program firmware or to set up other features. It can be used for servicing, to read out fault codes and to run test routines. It can be used for end of life, so probably the best example of this is there's a whole standard on end of life deployment of airbags. You actually use diagnostics to tell the car to blow its airbags so that you can dispose of the car. Airbags are like little rocket engines and you don't want to crush those because it could be dangerous. And for forensics, so most vehicles nowadays actually have a black box inside. It's recording data all the time. If you crash the car, then there will be some data potentially stored in there, and you would access that data via the diagnostics interfaces. So it allows a wide range of features, a ton of stuff, but it requires specialized tools. And typically the way this works, you take your specialized tool, like the Tech 2 for GM, you plug that into the OBD port under the dash, it has all the connections you need to get on the right buses, and then you start pushing buttons on the tool, and the tool knows how to do this communication, so you just push the button for, reset this to 0 this sensor or whatever, and it takes care of the rest and tells you OK or failed, and that's it. And if you're a technician, that's as far as you need to know. You just use the tool and you're good. But obviously, we're going to go a little further. So automotive diagnostics. I think it's a really cool topic because it probably presents the largest attack surface for the in-vehicle network. Again, there's that operational data. You can send that all the time. But this is like actual protocols, client-server stuff. There's a lot more that can be done here. And there are a lot of standards, like many standards. I wish we could talk about all of them, but we can't. J1979 is also referred to as the OBD2 standard, and this is used for mostly emissions purposes. It was standardized originally as OBD by the California Air Resources Board for the explicit purpose of doing smog testing on vehicles. Now it's used for a couple other things. You can buy really cheap tools for it. J1850 is a really ancient protocol used up to about 2006 in some American vehicles. ISO 9141, which is K-line or Keyword Protocol 2000, that's used for still some diagnostics, but less and less. And then there's sort of the big one we'll focus on, which is ISO 14229, or Unified Diagnostic Services, or for short, UDS is what I'll refer to it from now on. And that's basically present in any vehicle made nowadays that you'll see. It's just become the most common and popular way of doing diagnostics. And there's many more. Like, there's a whole standard just for like the size and shape of the connectors and things like that. Automotive industry loves its standards, but they don't always like following them exactly. Speaking of standards, the OSI model is just a useful reference tool I'm going to be using as we build up these picture of this. So many of you have probably seen this. General idea, at the very bottom we have the actual physical stuff that's happening on a wire, on a piece of glass, ones and zeros. And then this works up through a number of things to get us to an actual application protocol. Think HTTP or FTP, where as a programmer you're actually interacting with that more to build an application. And we're going to kind of put all the pieces in to figure out how this works. At the very bottom we have CAN, and I explained this sort of briefly before, but the basic idea of CAN, you have a bunch of controllers. These are your ECUs. Each one is a node on the network. Then you have a bus, and so you have a collection of these controllers, and they're all just connected to the same wires. This is not a star network. This is not a switched network even. It is literally, imagine 2 wires, and then you have ECUs just connected to them as they go through. It's really cheap to do this way. You don't need to run a bunch of cable. You can design nice wiring harnesses. But obviously it leads to some of the security problems we were discussing before, like denial of services. A frame is the protocol data unit we're interested in. It has an ID, a type, a data length code, and some data. We really only care about the ID and the data for today. So the ID is a number for standard CAN frames just between 0 and 7 FF hex. And that tells us what this frame means. Then you have the data, which is just up to 8 bytes of data, in this case some dead beefs. And that's your actual payload. There was a problem with this. You only have 8 bytes. And if you've ever tried to update firmware 8 bytes at a time, you know that's not a good idea. It will be very slow. So we'll have to fix that, but we'll get there. CAN actually takes up just the bottom of this stack. So it's dealing with the ones and zeros, the symbols on the actual bus, and it also deals with addressing and arbitration. So chunk that in at the bottom, CAN. It's got an ISO number if you want to actually read the whole standard. But then we get to ISOTP, which is what this is usually called. It's got a few different names. And here's the problem. How do we encode a 17-character VIN if we only have 8 bytes? You can't. And how do you send firmware, like several K of firmware or even megs of firmware? Well, that's even worse. So we need to combine these frames into a longer thing. And this is what ISOTP does. It allows up to 4,095 bytes at a time. So you can send a single request of up to 4,095 bytes. You will get back a response of up to 4,095 bytes. And it also has a flow control mechanism built in. This allows you to do things like request only certain sizes of blocks or request a separation time of a certain amount, which is nice if you have limited memory or limited processing power. And automotive controllers almost always have limited memory and limited processing power, so that's handy. It's also called CAN-TP sometimes. It's ISO 15765 if you care about the standard numbers. But it's just used to go from frames to blocks that are up to 4,095 bytes. So we can sit it in our model on top of CAN. And then we get to up to the application layer. And there's a few different things that can happen here, but we'll look at 2. OBD2 is present in basically every vehicle made since 1996. Definitely any vehicle since 1996 that was sold in the US. And there's actually 3 different protocols, or physical protocols you can do OBD over. I'm only going to talk about the CAN one today because we don't have time. But the way that this works is you can read some parameters. These are called PIDs, or parameter IDs. This is things like vehicle speed, engine RPM, O2 sensor temperature, so on and so forth. These are mostly meant for the purposes of doing smog testing, remember, so the data you get is a little bit limited. It was mostly meant for that purpose. You can also clear some fault codes using this, which is handy. If your check engine light goes on, you can turn it off. And you can get a full list of PIDs. Honestly, Wikipedia has the greatest resource for this. You can get every single one and all the modes. It's all there. And if you want to do this on the cheap, you buy one of these cheapo Bluetooth dongles with a fixed password of 1234. As we talk more about the things that you can do over the exact same port, you will understand why you probably don't want to leave that plugged into your car. Because, you want to trust whoever's connected to that device. But the basic way OBD2 works, you have a session, looks like this. You make a request. You send some bytes. You send a mode byte, which is which actual part of the standard you want to use. There's request a PID, there's request an extended PID, there's another set of them. There's a clear fault codes one. There's also one to request trouble codes, so you can actually request problems. You'll get back a response. It's the mode plus OX40 to tell you that it's a response. You get the PID that you requested, which is just an echo, and then you get your data. And that's about it. So you look at that big list, you see all the things you can request, and you can get some data out of your car. It's not that exciting for a security person, though, because all of this is just give me some data, and the only real action you can take is clear fault codes. There is a feature in there, actually, that lets you run like test routines, but I've never seen anyone implement it, so not that exciting. So let's get to the exciting one. Unified Diagnostic Services, which is also called UDS. This is the client-server protocol that's used for diagnostics in basically all cars today. The client in this case is a scan tool, which by that I mean the thing you are plugging into the OBD port. And the server in this case is the ECU, which is the actual controller in the vehicle. It defines 4 functional units containing a total of 25 services, and we will go through them and kind of just highlight the fun ones. And it's also available from the ISO folks as a PDF. You do have to shell out 198 Swiss francs for a PDF document, which kind of sucks. But the worst part of that is that you just get a PDF, and you can't execute this PDF. It doesn't really do anything for you other than tell you the standard, so I'm kind of stuck. And this is a problem that you've seen in the automotive industry a lot, which is if we don't have tools that make it easy to do this, no one really takes a look at it, and then a lot of the security is just obscurity. It's just no one's going to look there, so we don't have to do a great job of security. Or just never even came up in a meeting. No one ever thought that it was a big deal. So as we are able to release more tools and open source some of this stuff, on one hand it means that more people can just do the diagnostic functions that are useful. But on the other, it means that security folks like yourselves can actually start playing with these systems and auditing them in kind of more detailed way. So that's kind of my goal, is to free this information. I can't just publish the PDF, which is why I wrote an implementation. So a UDS session looks a lot like an OBD session. The only difference is instead of a mode, we call it a service ID. This is one of the 25 services. And then depending on what service, each one has its own parameters. This, again, depends on which service it is. They can be variable length. You have to look at the PDF to get that information. The response that comes back is your service ID plus 40, and then the response parameters, which, again, depend on exactly what service it is, and you know how to decode that based on the standard. It's, again, pretty simple to do. The hardest part is actually knowing what these parameters are. And the only other thing that can happen here, actually, is you can get a negative response. So if the controller decides it doesn't like you, you requested something it can't do, or you don't have the right security mode, or whatever it is, it will come back and say, negative response, go away. So that's UDS. You send a request, you get a response. Pretty simple. And that sits, again, at the top. We have OBD2 or Unified Diagnostic Services at the top of the picture, ISOTP, which lets us chain frames into blocks, and at the bottom we have the actual frames that are the physical representation on the bus. So there's all of our pieces. But now we're going to dive into UDS because I said it has 25 services. It's important to actually take a look at what they are. This is the first functional unit, and I am going to try to make this as exciting as possible while having a big list on the screen. Basically, I'm going to go through why these are actually interesting to security folks. We'll start with diagnostic session control. This one is really just a prerequisite for many things. So often you'll have to move a controller into a diagnostic session or a programming session or something like that, which just puts it in a special mode where it might disable certain features because it knows you're going to perform diagnostics. It's also used sometimes to access the bootloader when you're programming. ECU reset lets you reset the ECU. Pretty simple. There are a few types of this. You can do a hard reset or a soft reset. It's kind of fun to do this while things are running if you know what you're doing, because you can make lots of lights blink and stuff. Security access is really the security feature that's used to secure all this. It deserves its own discussion, which it will get momentarily. We'll skip over that for now. Communication control allows you to enable and disable communication from an ECU. This is useful if you're actually an OEM who's designing the tool, Because if you want to update firmware on a CAN bus, you want to have as much bandwidth as possible to do the update as fast as you possibly can. And this means you don't want anyone else talking while you're trying to do your firmware update. So you can tell, let's say, everyone else on the bus, please be quiet, I'm about to do a firmware update. And that operational data will go away. Now, this is potentially useful to an attacker because if you can make that operational data stop from one controller, you can inject your own frames. You can do this anyway, like in the demo we showed before, by really spamming frames onto the bus. But sometimes you'll end up with issues where you won't quite overrun the buffer correctly or whatever, and you'll get blips where it will receive a valid frame and it will reset a state. Doing this, you're actually able to make a controller completely stop talking. It also gets around problems like a sequential counter in the CAN frame where you can't easily inject. So communication control is kind of interesting for that. Tester present just tells the ECU you have a tester there and stops it from timing out. Access timing parameter is used for some timing settings that honestly I've never really needed to deal with. Secured data transmission, I've never seen anyone use this, but it's a kind of nice idea. Basically, it just is its own service, and it's like if you want to implement your own secure transfer, you can do that. This is just a way to transmit a whole block at once. And it just doesn't frame anything at all. Control DTC setting lets you enable and disable whether a ECU is going to set trouble codes. This is interesting, well, it's useful whenever you're doing testing where you're going to say, do that firmware update, you're going to make all the controllers stop talking. That's going to set a bunch of fault codes because those controllers are expecting those messages. So what this does is it says, okay, don't worry, there's no problems right now, we're just doing a firmware update, don't expect any failures. Could be interesting though if you're doing an emissions test and you don't want any failure codes to come up because you can just disable them being set and the check engine light won't come on until the car is actually reset. Response on event, this is something that allows you to set up some special events and then when they occur get a response back. It's not, I've never seen it used in practice in any tools I've used. And link control lets you change the baud rate. And that's kind of not interesting unless you want to do a denial of service attack. And potentially you can change the bit rate that something's communicating on and crash the whole bus. But that's just sort of fun. This is all just the stuff that makes diagnostic work. This is like the foundation of being able to set up your sessions and do that sort of thing. The next parts are actually the more useful bits. And read data by identifier and write data by identifier. If there's two services you should be interested in, those are probably them. There's a database of these data identifiers in the vehicle or in the ECU. And they all just have a number that's assigned to them. And that has usually a specific representation based on either the OEM that made the car or whoever made that actual controller in some cases can define them. And what those contain is just some arbitrary data. You don't really know what's in them, but you can read and write them. And if you use a real diagnostic tool to, let's say, read the odometer out of a car, it will do a read data by identifier for that data identifier, and it will pull the data out and decode it and show it to you. So what's nice about this is if you can figure out how these tools work, you can do your own implementation to mimic that functionality and do it yourself. Write data by identifier is even more cool because it lets you change things like VIN numbers and odometer values. This is usually secured for good reason, but it is there and it's often the way that parameters and calibrations get changed. There's also read and write memory by address. And yeah, that should just sound concerning immediately because being able to access arbitrary memory addresses is not going to be very safe. This is hopefully not enabled in production. I have seen at least read memory by address enabled on controllers. I am a little scared to try writing all sorts of memory by address because you can see if the service is enabled, but you can cause some really bad things to happen if you just overwrite random memory in your airbag controller. You might blow the airbags. That is a thing that could happen. So those ones are scary and hopefully aren't enabled. Scaling data by identifier just gives you some information about how these data identifiers are converted to engineering units. And read data by periodic identifier lets you say, please send me some data on some period. So you can say, I want this every 10 seconds, give me the current value of vehicle speed, and we'll send it back. Last one there is dynamically defined data identifier. There's a lot of these. That one allows you to actually set up your own special data identifier and give it like a memory address range that you want it to read, which is potentially, if they've disabled read memory by address but haven't disabled that one, that's potentially a way to get in. So these are quite interesting because you get access to a bunch of parameters, both reading and writing. For data trouble codes, this is useful if you're trying to fix a vehicle. You get the stored data functional unit, and what this does is clears fault codes and reads fault codes. OBD can do this as well. This is a bit more detailed in the fault codes you get out of it. So you do need to know a bit about the system to actually know what these mean, but you can read and clear them. If you're fixing a car, it's interesting. If you're trying to hack a car, maybe less so. We have input-output control functional unit. This one really should be disabled in production. It just allows you arbitrary control over pins of the device. So you can actually say, I want pin 6 to go high now, and it will let you do that. Very useful when you're trying to test a device, but a little scary whenever you're actually trying to use it. You wouldn't want someone to arbitrarily be able to just change the GPIO levels on an engine controller or an airbag unit or anything. That would be not good. So this should be disabled, but it's at least something to look for and scan for. Routine control is another very interesting one. It gets its own functional unit, remote activation of routine. And this just lets you run arbitrary routines. There's a 16-bit routine identifier. You pick a number and you say go, and it does something. And it's used, for example, one place that it's used a lot is in programming ECUs. There's a routine, it's a standard routine for erasing flash. So this will erase the flash memory. I was talking about bricking cars earlier. If you do that, you will end up probably with a engine controller or whatever that doesn't work. It usually is a secured function, so you are less likely to do it by accident. But if you just run a bunch of routines, that could happen. The other place that this is used is in servicing and testing. Probably one of the best known examples. If you remember back in 2015, there was the car hacking thing where they were able to remotely take over the vehicle, and then they also did things like apply brakes. I believe the applying brakes work that was done, or actual attack that was done by Miller and Valasek, that was done via using a routine control. The reason for this is if you're a mechanic and you need to bleed the brakes on a car, don't know if anyone here has done that, but you have to get your buddy to sit in the driver's seat and push on the brake pedal while you turn the little things on the brake caliper, and it shoots out fluid and air, and then you do that till there's no more air in the system. So there's actually a routine you can run that just applies brake pressure for you, and that way you don't need your buddy to sit in the car. The only problem with that is if you activate that on the road, then it applies the brakes, and that could be a problem. There's usually restrictions on when these can be activated and things like that, but then you can get around those by forging data. So these are really concerning. If you have access to a vehicle's network, routines are probably your best way to just cause bad things to happen. And again, there's a ton of these. Some of them are defined by the OEM. Some will be defined by the tier supplier. And I've seen some cases where there's some that no one really knows what they do. And that's a real problem with this diagnostic stuff, is things can get left into firmware. The last one, we're almost done with big lists, is the upload-download functional unit. And this is just how you write firmware or read firmware. You request a download or an upload depending on if you're reading or writing. You use this transfer data service to just shoot blocks of data into the controller. And then once you're done, you request a transfer exit. Usually the actual update process is a bit more involved. You have to change states and reboot to get to the bootloader, and then you do this transfer data thing, transfer some data over. You might have to read back some verification and write something to say that you updated the version. It's a little bit more involved. You're less likely to be able to guess the exact process, but if you have an official tool that can do a firmware update, you can reverse engineer the process pretty easily. So let's talk about security access, because this is a security conference after all, and that's the only service with the word security in it. And it's what's used to secure anything that could be bad. And this comes from a standard that's existed for quite a while. So what they wanted to do is make sure that a random person couldn't plug in and just be able to run these services. It's a challenge response mechanism with some weird terminology. So the way it works is you request a seed from the ECU. And this is meant to be a random number or a nonce, just something random. It responds with that random number. You then send a key, and this is the one place where like that is not the right word. That should be a response, but it's called a key. You send the key back, and then what the ECU will do is compare the thing you sent it with what it calculated based on the random number and some magical algorithm. And then if it was good, you sent the right thing, it will say, cool, I'm unlocked now. If it was bad, it will give you a negative response saying, you got the key wrong, try again. And yeah, that's exactly really how all this ends up working. It's just, request, response, unlocked, done. Once it's unlocked, it stays unlocked typically until you reset it. So you can use a tool that can unlock this and then unplug it halfway through it doing its thing, and the ECU stays unlocked. Also, there's no integrity to anything you're sending back and forth during this session. They may have implemented that somewhere along the line. Maybe the firmware is signed and their bootloader checks a signature, but the actual protocol doesn't implement anything like that. So, once it's unlocked, you're in. So there's a few issues with this. The confusing terminology is one that I think has led to some problems. A challenge response, right? The actual secret sauce that you do on the challenge to make the response, that they call the algorithm. We'd normally call the algorithm something like AES, let's say, or something like RSA would be the algorithm, and then we use a key as the secret bit to put into the algorithm to actually make that happen in a way that is secret. But they decided to make the algorithm the secret part, and this is kind of textbook security by obscurity stuff. So the terminology might have been one thing that led to some bad algorithms. There's other challenges there, but the algorithms are typically bad. We'll get into a couple of them in a moment, but they're typically very simple. So you'll either often have a very simple algorithm that uses a random number, or you'll have a static seed. So this is an ECU that just always sends you the same random number. It is a random number in the sense that every ECU will send a different one. So if you have 100 cars, all those engine controllers in those 100 cars will send a different number. But if you take one car, it's always the same number. This is a problem for two reasons. Well, the real problem with this is you can brute force it pretty quickly. This was done, again, back in 2010. They showed you could brute force this in a matter of days. And once you have it, you're in. The next one would be a small key space. Usually this is 16 bits, 2 bytes. That's a small key space. There's probably a reason which it got to that, and we'll go to there. But there's two problems with this key space. One is you can brute force it really quickly, obviously. The second one is if you have a valid tool that can generate the key response, you can actually brute force the entire key space out of that tool. So what you do is you pretend to be a car. You plug this tool in, and you say, all right, give me the response for seed 0. Give me the response for seed 1. And you just go all the way up to FFFF. A lot of these tools work offline. They don't have any connection to a backend. So what you end up doing is just creating a map of 65,365 values to a different set. And now you have the whole key space, and you're done. You're in. And that's clearly going to be an issue. If someone can do that, they're forever have the algorithm. And we have an example of that. Then there's a lack of privilege separation. The spec allows you to have multiple security access levels. And the idea here is maybe one is for programming and one is for diagnostics that a service technician does, and one is for end-of-life deployment. Often the only one that's separate is that end-of-life deployment, and that's only because a standard specifies that it has to be a separate level. Everything else, they just use kind of level 1, and once you're in, you get everything. That's not necessarily across the board, but the general case I've seen is there's only one security access level. So no separation of privilege. Once you have a controller unlocked, you can do most of the things. I think a lot of these issues actually stem from the standard, and this is actually a screenshot of the PDF. We'll call it fair use if anyone from the ISO is here. It's telling you you have a request seed, you're requesting 01, you get the function to send a key is 02. They give an example with a 2-byte seed, and then they give an example calling it the key of the server that comes back, and it says it is a 2 complements of the seed value. So the actual secret part here is just that you take the 2's complement. That is the top secret key. That's just obscurity, that's all it is. But that has found its way, maybe not that exact algorithm, but that kind of thing has found its way into a lot of vehicles. And this is really an example of just kind of the spec, maybe just giving an example as just a simple, here's how it could work, and people going, oh, we'll just implement that. This is a real algorithm I have seen on a real ECU that is in probably millions of vehicles. I won't say which ones, but you get the key 0, the first byte. You just take OX45 and subtract the seed value from it. This wraps, so if you get to 0, you go back to FF and just unsigned subtraction. And then key byte 1, take OX43 and you subtract the second byte. That's it. And that's how it is for all of those parts around the world. There's a lot of different ECUs, and a lot of them will modify these numbers, which is why I'm not terribly concerned with telling you these specific ones. But that's the kind of algorithm. It just takes some bytes, subtract some numbers, and you get the key. So yeah, there's a lot of issues with security access, and there's a lot of features you get. The biggest problem here is these are out there. There's millions of these on the road, so those aren't going away. You can't really change this. And hopefully we get smarter in the future about how we do this security access thing, despite the challenges that are out there. Let's talk about tools. I really like tools. Some folks are more into releasing exploits. I think with automotive, there's so much that we haven't touched just because the tools are kind of hard and out of reach that, it's not really an exploit in some cases. It's like you just find a service that's sitting there. It's like hacking back in the 90s whenever you would just find broken things lying around. Not that we don't still see that, but the tools for doing this. A real scan tool, there's 2 types. There's the one that costs you a lot of money and has all the manufacturer's special codes in it, like the GM Tech 2 or a Snap-on Solus Ultra, whatever. Then there's a cheap option. These usually only do OBD, but a lot of them can do UDS if you know what you're doing. The Elm 327 tools, for example, those just implement ISOTP basically with some problems, but more or less they're just doing the CAN level ISOTP. If you know what data you need to send to it to do a read data by identifier, it will receive the data back and give it to you. The biggest issue you run into there is that they have very limited buffers, so you'll end up just filling up the buffer and getting crap back. Also, those tools tend to be a pain just with the Bluetooth serial link is not great. USB to CAN adapters, there's a bunch of these out there. I made one I presented here a few years ago called CANtact that's open source. This does CAN, but you still need ISOTP, you still need UDS. How do you get that? And this is the tool that I've been working on, which is Pivot. It's a Python vehicle interface toolkit because I like acronyms that sound like words. And it does CAN, ISOTP, and now UDS. So this is a Python module that you can use to actually talk to these controllers. And you can also use it to do some other things with log files if you don't happen to have a car beside you, like I don't right now. It's open source. It's on GitHub. There's a link at the end of this. And it's available now. And you can have some fun with it. So let's do a demo. And I'm just going to do some examples and then more of a practical demo. So the examples, we'll start off with just doing some stuff in IPython. So if you ever used IPython, I don't know if there's many Python folks here. IPython is a very nice interactive REPL for Python. It's got tab completion, makes your life easy. Once you set up an interface, which there's a few lines to actually set the thing up and tell it the right IDs and the right bit rate and all that junk. But once you have this UDS IF for UDS interface, you just go UDSIF.request. The service in this case, we're going to do a read data by identifier, and we're going to do a request, and we want data identifier F18C, which is the standard one for ECU serial number. Just happens to be. And what we'll get back is actually a Python dictionary that has the response parameters. So we get the data identifier back, and that's actually coming back from the server. And then we also get a data record, which is some serial number that we got back. It's pretty simple. But in other cases, there are tables that are in this standard, and I really didn't want people to have to buy the PDF. So I have implemented some of these tables. For example, if you're doing an ECU reset, there's a bunch of different types. So you can do the request, and then you can do reset type dot hard reset. It's very nice to have tab completion for this because I can just go through and go, ECU reset dot reset type dot tab, and then the whole list of them comes up, and you select one, hit enter, and you're good. And then we get a response back, reset type 1, which is hard reset, and we're done. This would be more exciting if we had a car to play with, but that works whenever you're connected to a vehicle and you have something to actually send you valid responses back. Next up, we have decoding. Let's say you have a log file. So how do you get one of these? Let's say you take a valid tool, a real OEM tool, you plug it into the OBD port, but you plug it in through a OBD splitter, which you can get for $1. And then on the other side of that splitter, you put your own tool, and you run, let's say, candump on Linux to create a log file. You'll get something like this. You filter it by ID to get rid of the other junk. This is a diagnostic session that's happening. So what do we have here? We have a timestamp. We have the interface, which is can0. We have a can ID. And we have some data. And standard log file type thing. So now we want to decode it. So we have in orange these ISOTP bytes, which are used for the actual flow control and things like that. We have a service ID, and then plus 40 are the response ones. Then you have data, which is in black. You have negative response codes in red, and this is really hard to do by hand. And as much fun as it is to look like a cool movie-style hacker and watch the frames fly by and be like, it's a diagnostic session control or whatever, you want a tool to do this. You don't want to try to do this yourself. So one nice thing about having an open source implementation of UDS is we can take log files and we can jam them in, and it can spit out Python objects, and then we can pretty print those, and we're done. So this is sort of a proof of concept right now. I would like to expand this into a bigger tool, but what that would actually come out as is something like this, which is a little nicer to look at. So you have a request. So there's a diagnostic session control request. We want diagnostic session type 3, which I believe is extended diagnostic session. It gives back a response, and it actually comes back with this parameter record. I have no idea what that means for this, but this was reading airbag data. So brings that back. This particular tool does the exact same request again for some reason. Then we have a read data by identifier. We request this thing. We get back 0513 as bytes. And then we request a different one. We get back this, which looks very ASCII-like. And it turns out to be that string, which is the part number of this particular ECU. This is not the part number that the security key thing I showed you was for, by the way, just in case anyone wants to try that. And then it reads some more data identifiers. This goes on for a long time, the actual process, but now we can nicely look at it and look at this as a dump. Again, proof of concept right now. Next step for this kind of tool would be to actually make it more like, for example, binwalk. I don't know if people use binwalk on a regular basis here. It lets you extract various types of data from binary files. I'd like something very similar for UDS, where let's say you have a whole firmware update trace. You just run it, and it will actually spit out a binary file of the firmware that was sent, because that would be quite useful. So yeah, that's a quick example. I will try to run one more for you, just to prove that this is actually a thing that works. If I can get my mouse over. Cool. So what we can do, so the example I showed you is this, and we just run this UDS log decode. Demo.txt is literally the stuff I showed on the screen. And we can cat demo. Yeah. These are the frames we're looking at. But then we can run this. And takes a second. Then, kicks out this. So what would you rather look at? That or that? I looked at a lot of the top one, and I'm very happy to be looking at the bottom one now. But just so it wasn't a contrived demo, we can also do a different car. It's probably a little hard to see, but the last two parameters there, so for the last one it was 6E0, and before that was 51C. That's the request and response IDs. So we can run this. This is from an Audi A4 crash data recorder. And this one's actually pretty short for a crash data recorder session. And we can scroll back. We see some interesting things here. It's doing a routine control. And sometimes it does a routine control and actually gets a negative response. It says request out of range. And what that likely is this particular vehicle, you might be asking for airbag data for airbags that are not installed on this model. It's probably what it is. But yep, it does some of that, does some read data identifiers, goes all the way through, and that was all the data that it ended up pulling out. From that, there's some fancy software that generates a nice report, but that is all the actual crash data that's located in the vehicle. So yeah, we can run that through on different examples. And you also should be able to do this live. So if you actually have a vehicle and you have a scan tool, you can plug in a Y-splitter, and you can push the reset steering angle sensor button, and then you'll see exactly what it's sending to do that, which is kind of nice because you just get real-time feedback. So a few conclusions here. First off, challenges. The folks in the automotive industry are aware of a lot of this stuff, and they're trying their best to fix it given the constraints of real life. So I don't like to stand up here and be like, oh, the automotive companies are terrible. They're trying, but the reality is it takes time and it takes money and effort. And you gotta turn profits somehow. So right to repair is actually a big challenge for them and a kind of blessing for any security person. It's really funny. If you talk to people in the automotive industry, they hate right to repair, and if you talk to anyone at DEF CON Car Hacking Village, they love it. What right to repair means is that the OEMs that make cars, they need to actually provide, at least in the States, all of the information that they would give to a dealership to anyone who is willing to pay a subscription fee to them. This means that you or I could actually sign up and get a real diagnostic tool that can change firmware in a lot of cases and do stuff like that. So that's clearly an issue. You can't put the secrets in your tool if you have to give your tool to anyone who's showing up with a few $1,000s. It also gives us some future-proofing here, because we know that they can't implement anything so bulletproof that we won't even be able to interact with the systems. There's limited hardware resources in these. Some of these still have 8-bit microcontrollers running some limited functions, and it's hard to do lots of fancy crypto on that. You are not going to convince anyone in automotive to spend a bunch more money to make a door controller that controls the window more secure. You won't. There's not a good value proposition for it. You might be able to get a couple security elements in the vehicle, but even that is pretty new, and that's kind of a limitation. The cost is the other side. Automotive is very cost-driven. Again, you're not going to get yourself a special ASIC for security in every controller. It just ain't going to happen. You have to deal with the fact that you're trying to get a car out that drives, and security is not necessarily the primary concern there. There's this problem of who do you trust, and the OEMs would like you to trust them. They would like to keep the keys and then dole them out. The problem is they then sort of have to trust all of their dealers, because their dealers have access to do this on any vehicle. And by extension of right to repair, they have to trust anyone who's willing to show up with a few $1,000s and get a subscription. So that model maybe doesn't work so well. A model that I would like to see is a movement to actually trusting the owners. So I give you a key that unlocks your car. If I also gave you a key that unlocked the diagnostics on your car, then you can do terrible things to your own vehicle, and that's your problem. But if you go into someone's dealership, they won't be able to do anything unless you give them that key. Now, there's a ton of practical problems with implementing that, and people lose smart cards and all that. But that is a model that I would really like to see in my kind of hopeful thinking about the future of this. And then there's legacy. Again, you have a lot of cars on the road. They implement some bad protocols. They will be on the road for the next 10 years. You just have to live with that. There's millions of diagnostic tools out there. You're not going to convince every garage to buy a brand new one tomorrow. You just can't get around some of those problems. A lot of money has been put into building out these systems and networks, and you can't just change them right away. But there is some future here. One would be Ethernet-based diagnostics, which is also called DOIP, Diagnostics over IP. This is a new standard. It's not really in any cars, or at least widespread yet, but it's coming because we're seeing automotive Ethernet become a thing. That's right, full IP in your vehicle. And someone once explained to me when I mentioned this that IP has never made anything more secure. I don't know if I entirely agree with that, but it's kind of true. I mean, usually when people start putting all sorts of network services up, the holes appear. So this will be interesting to look at, of course. there is better security access stuff coming in. And I have had people from engineer up to CISO at various companies tell me that they are developing new things. They have yet to actually tell me what those do, so I will reserve judgment until we get to see what they've done. But they are trying to address that problem. Again, they have the challenge of you need to trust a lot of people. So it's hard to do that right. And then future work on this kind of tool. Now that I have this UDS implementation, I want like all sorts of I want a fuzzer and I want a scanner and I want like this tool to walk through logs and pull stuff out. I think it's fun stuff. It makes us more accessible. Hopefully we will get to play around with it a lot at the DEF CON car hacking village this year, which I'm stoked for. But if you have any ideas in terms of what kind of tools would be good for you, what problems you're having, happy to chat about that kind of stuff. Anyway, just to finish off here, give some thanks. Thanks to the Black Hat folks for having me out here for the 3rd year in a row. It's been fun every time, so I'm glad to be back. And of course, thank you to all of you who took some time to hopefully learn a thing or two about cars. Hopefully it was interesting, but I'm happy to chat more. We have about 10 minutes now, and also if you can find me in the hallway. Lots of information there, GitHub, you can install it from pip. You can email me there, you can Twitter me there. More information with link layer is there, and the Tretis information is on that one. So thanks, and yeah, any questions? Yeah, go ahead.
So, just curiosity. So the problem you presented are basically the problem that you encountered during your work, I guess.
Yep.
And so the question is, how much of the things you show are actually like real threats, like that you have like in real car? Because I mean, one thing is the protocol, that there could be some problems in the protocol. Other things is the implementation. So the surface, there must be the surface of these problems.
Yeah, so the question was, questions like, where does this come up in practice being a threat in cars? Yeah, so one example was, of course, the brakes thing, so being able to do a routine control for the brakes. Another is simply changing firmware. There are, I'd say the majority of cars on the road today have no firmware signing. So if you can do that process, you can get code execution on an engine. And then you have like an implant, basically. You also can modify things. Actually pulling that off would be probably pretty hard because you would need to reverse engineer the actual firmware, which has a ton of stuff compiled into it, and figure out how to insert your own code. But it is possible. The other side of this comes into fraud. Things like odometers that can be reset, VIN numbers that can be changed, or even in the case of the data identifiers for diagnostic data, or for crash data. Potentially, you crash a car, and if the insurance company decides they want to send a forensic person out, you could change that data. So there are some real threats there. But in terms of attack surface, if you want to establish any sort of persistence in the vehicle, this is going to be the only way to do it on the CAN bus, as opposed to, unless you're taking over something like an infotainment unit. So this is about a bit of a lower level, but it also is the controllers that really affect safety critical items. And to be honest, I don't know that every single OEM knows the full set of diagnostic features that is present in their controllers. Suppliers leave some in, things get left on. It's like any other network service. It can be configured wrong, and then suddenly there's holes that appear. So,
I also have a follow-up.
Yep.
Because is there a way to connect to the OBD port externally, like from the car, or you should break into the car because the connector is in the car?
So the follow-up there was, how can I connect to the OBD port externally? Some vehicles have known physical flaws that you can get on the CAN bus externally. Maybe not quite the OBD port, but some CAN bus, and there'll be controllers there. If you can't do that, you probably are going to be breaking into the car or cutting a hole in the window. But then, of course, you have to look at the whole range of attacks on things like infotainment systems, tire pressure monitoring systems that have wireless interfaces. Because if you can get code exec on one of those, then suddenly you have your own diagnostic tool in the car that can do all this stuff. So this might be like kind of a privilege escalation to compare it to normal IT, where you go from being able to run code in a bit of a sandbox that can just maybe send and receive CAN frames, to actually being able to run routines, diagnostic routines on a controller. Yep. Rob?
You showed us an algorithm to compute a key in response to a seed. What do you do to find it out? I mean, it's an incredibly simple algorithm.
Yeah.
What steps do you follow to find it?
So to find the key, the seed key algorithm I showed you there, pretty simple. I actually had a valid tool that I borrowed from somebody that was able to generate those. And then I just threw a bunch of seeds at it. And I thought I was actually going to have to do every single one until I had about 3 of them and realized that there was maybe a little bit of a pattern because I was doing them incrementally, and of course the seed value was going up incrementally, and I was like, the seed went up incrementally, the key went up incrementally. I was like, this is not right. And yeah, turns out that's what they use. There may be some that are more complicated that might use things like the serial number to encode that, but once you have the ability to pretend to be a car, you can forge any of that. So you can fuzz the entire key space of whatever it's possibly using to generate that and get all those values out. Yes?
Regarding to the security access, it's only sent to the ECU you want to talk to, or is there like a gateway that you send to, and then after that you can access any ECU?
Okay, so the question was, with security access, is it only sent to that ECU that you're unlocking, or is it sent to a gateway that unlocks and lets you access past it? So by the standard, it's actually unlocking the ECU you're talking to. It's putting it into a special state where security is turned off, or you have security access. In actual practice, though, there are sometimes gateways that exist where, for example, you'll send a CAN frame in, and it will first hit a gateway, which then is going to take that and determine what CAN bus it should be sent on. Maybe this does 2 nice things. One, it lets you, actually have multiple CAN buses that only need 1 OBD port. And secondly, if you plug in like some sketchy dongle and it crashes the CAN bus while you're driving, it's only going to take out the part of the CAN bus that's between the OBD port and that gateway. Everything else will be safe. And that's kind of important because things like power steering will turn off if you crash that bus. So Volkswagen, for example, has a system where the OBD port goes into a controller, and the only thing that's on that bus is the OBD port and this controller, and everything else is gatewayed. But that typically doesn't have so much to do with security access as it does just with physically separating buses. Yes?
There are tools like the Wireshark that allow you to record all this communication and see offline, like data frames and stuff like this.
Yeah.
Or even replay it later, like when in the middle of Rockstar stuff.
Yeah, so the question was, does Wireshark or something like that let you record this? And I would really like this to just show up in Wireshark, because Wireshark's great, and you can just click things. And actually, Wireshark does have support for CAN. On Linux only, but with Socket CAN, you can actually, just like any other network interface, you double-click CAN 0, and you're getting CAN frames. Works quite nice. The reason that I didn't write this as like a Lua plugin for Wireshark is because that would only really work for receiving. Wireshark doesn't work so well for transmitting stuff. That wasn't quite enough for me. I wanted to be able to transmit. But it probably wouldn't be that hard. Now that I have everything broken out into bit selection, all that, and all the tables and everything, it probably wouldn't be that hard to port to something like Lua and then be able to decode it and actually get that display in Wireshark, because I'd much rather do that than write my own GUI, because writing cross-platform GUIs is not fun. So, cool. I have 1 minute. Any last questions? We're good. All right. Thank you all very much for taking time and being so attentive. I'll be around, and feel free to chat about cars. Thanks.